dynamic systems. So for dynamic systems, the independent variable is time. And time has only one direction. Right? In physical system, you cannot go back to time, even though you can see the movie, the fictions say, okay, we can go back to the past, right? But in our current experience, time is going on. Okay? So when time goes on, the system evolves. So now, so I have to say that I use, instead of x, I use the time t, okay, to describe the system. Okay, now, so we have a special kind of ODE, and we call it autonomous ODE. Y term is equal to f of y. Okay, and for here, so we have a solution, okay, which is constant as time evolves. It will stay in the same value. Okay. Right, and so here, this is time. Right, so I draw the direction 0. Now, this is the solution. So according to the drawing of direction 0, a possible solution is going this way, and I put the error 1 because time goes on, always goes on to the right hand side. Okay, so the solution is only possible to go to this equilibrium solution. Right. If you have a solution y equal to 2, right, it is unstable. Unstable. Why? Because if you have a little bit error or noise, then you will go out. And when you go out, then the solution will go up and leave this equilibrium solution because the slope solution is this way. Or you will leave the equilibrium solution this way up to here and then converge to this stable equilibrium solution. Okay? So everything going on this way is because this is the time. And time always goes on. Never go back. Never go back, okay? So this interpretation is valid only if the independent value is 10. Okay, and when we're talking about the dynamical system. Other questions? Okay. Section 1.6 is about orthogonal trajectories, and it is just for you for self-reading, because I don't have enough time to teach this part. So please read over the textbook. And this subject is very interesting. And I prefer to talk about the existence and uniqueness of solutions for initial value problems. For given general theorem, I would like to take several examples. So the initial value problem okay. So this one is an ODE. This is the initial value, initial condition here. Now, this equation has no solution, right? Because this is because that the trivial solution is the only solution for this ODE. Because you put the x value here, right? And x value is never negative. So if you want that this is sum equal to 0, the only solution is y is equal to 0 for all x. No other possible solution you can have. Okay? So y of x equal to 0 is the only solution. But we have an initial condition which says that y is 0 equal to 1. So it's impossible. Okay? Okay, so this one tells us that we only have trivial solution. But this initial condition excludes this initial condition. So turns out we don't have any condition. Okay, so there is no solution for this initial value problem. Any questions? First example. The second example. Now, this IVP has precisely one solution. It is very simple. You just take the integration. And so you can find one and only one solution to satisfy this ODE as well as the initial condition. Okay? The third example. X times y prime equal to y minus 1. That's infinitely many solutions. So you can check that this IVP has infinitely many solutions, which is 1 plus Cx. So C can be any. Real numbers. Okay, so you can see that the initial condition is satisfied automatically because when we put x equal to 0, this is 1, always 1. Okay. Now, we can take the derivative. So you can check that. Because y prime is equal to c, right? Oh, equal to c. Oh, equal to c. And so, x times c equal to y is 1 plus cx minus 1, so it's equal to 6. So it's an identity. So of course, it's quite easy to check. This is a solution for both the ODE and the initial condition. Okay? So it is very easy to check. So now you have infinite remaining solutions. So the first example tells you that you have no solution. The second example tells you that you have exactly one solution. And the third example tells you that there are infinitely many solutions for the initial value. Okay. So now, I would like to address a general result, okay, regarding to the existence and uniqueness of an initial value problem. All right, so consider the first order ODE and this ODE, of course, is in the explicit form. Okay, with an initial condition. Okay. Right? So we consider first order ODE together with an initial condition like this one. And recall again. A region X is an open, connected set in the XY plane. Okay. So remember we mentioned a region before. It is an open, and open means without boundaries, right? And connect means that any 2 points in your region, you can always draw a path, right, to connect. So that. Okay, so now I state a theorem. Sequence numbers A, B, C, D means extra theorems in addition to any theorems in the textbook. So quite often in the later lectures, I will give extra theorems, okay, as supplements to the material in the textbook. All right, and I call it the existence and uniqueness theorem for first order initial value problem. Alright, so the statement is here. Let f of xy. Okay, so let f of xy in this ODE be a bounded continuous function, okay, in a region S of the xy plane and E. So this bounded means that we can find a positive number such as that all the function values has x value less than or equal to m, okay, for all points in this region. And x is 0, y is 0, x0, y is 0 is a point in the region. Yes. Alright, so first of all, we describe this function, f of x. So it is continuous and bounded in a region, right? In the xy plane. And in S, f satisfies the Lipschitz, right? So Lipschitz. Just a name, okay? The Lipschitz condition. Okay, the Lipschitz condition is here. X plus 1 minus f of x by 2. Okay, so the difference between two function values, okay, they have the same x coordinate, but they have different y coordinates. Is less than or equal to a constant n times y1 minus y2. Two points. X, 1, 1, and 1. Okay. All right. So we describe this function. Okay. It is bounded, continuous, and it satisfies the Lipschitz condition. Here. Right, then an open interval minus 0 exists. And on which, okay, there is one and only one continuous function y of x is continuous derivative. And I is 0. Satisfying. Then all E 1. The initial condition. So let me draw a picture to illustrate the situation. Because f of xy is a function of x and y, so we have to draw a three-dimensional. Now, the region might look like okay, so this is our region. And okay, we have x is 0 here, and y is 0. So this is point x is 0, y is 0. So x 0, y 0 is in this region. And we can find in the x-axis, we can find an open interval. So, so here, this is x0 minus h. This is x0 plus h. And we have and here we have y0. So this is the okay. So it's and we can So we have so this point x, y, 1, this point x, y, 2, Right. So the situation is that in this region, the f function is bounded and it satisfies the Lipschitz conditions like this one. Then we can find an open interval. So we can, and also we know that x0, y0, this is concerning to the initial condition, right? Is in the region here. Alright? And then we can find an interval, okay, x0 minus h up to x0 plus h in the here. And the corresponding y-axis, this is y0, and the y0 minus nh, y0 plus nh here. Okay? And so this rectangle, so we now have a rectangle. In the region. Okay? And in this rectangle, our solution will be here. So we will have a solution, and you can draw it like. So it's possible that our solution is this is the value, and so here okay. So this is our solution. And goes to this point. Okay. So this is the situation. Right? Let this go. So this is our solution. And this solution is unique. Okay. And so we have one and only one solution. And this solution is continuous and has continuous derivative. But do you have any questions about the picture? Any questions? This is the general idea. Okay. So the question is that everything is for the function f of x, f of y. So you have to find a region x in the xy plane. Okay, you find a region of R which is open and connected. And you find in this region the f of xy function is bounded. Okay, so you can find a positive number m. So value will be bounded by m. This is the first condition. And the x0, y0 is in this region. The second thing is that in this region, f of xy satisfies the Lipschitz condition. This is the Lipschitz condition. So that if you are given x, okay, the same x but different y, then the difference of the corresponding function value should less than equal to n times y2 minus y1. So this is always true. This must be true. So the difference should be upper bounded by a constant n times the difference between y1 and y2. Okay? If this is true, if both conditions are true, then there exists an open interval, right, around x0. Okay. So we have x0 minus h up to x0 plus h. Okay. And on this interval, there exists a function, a continuous function y. Okay. And very interesting is that the value will be in between y0 minus nh to y0 plus nh. Okay, so the value of y of x will be confined into this interval. So basically, the graph of the function must be in this rectangle. Okay, confined into this rectangle. And this is one and only one solution. And now I can give to you that this part give you the existence condition. Okay? And this part give you the uniqueness. Okay? So later on I will write a more specific theorem provided by the textbook. Right? So this part will say that there exists one solution. But only this part, we cannot guarantee the solution is unique. Okay? Only this part says that there exists one solution, at least one. So to have unique solution, we must have the Lipschitz condition. Okay. So any questions about the statements of the general theorem? Okay. So as I said, this part is needed for existence, and this part, the Lipschitz condition, is needed for uniqueness. Okay. Okay. So. right? This is so maybe I think I write in mark here. One. If f of x, right, is bounded, is a bounded continuous function. Okay, so if bounded continuous function in the origin, rectangle or 0. Oh, I'm sorry, it's x. No, I use x, right? Yeah, I'm sorry, it should be s. The rectangle means x. Okay, so suppose specifically, if f of x, y is a bounded continuous function in an open rectangle, okay? So this is a rectangle. Ready? Then the IVP has this one solution. Y of x which exists at least for all x in the subinterval of I want to take this one. Right here. X minus x is 0. This is a where alpha is equal to the minimum of a and the b divided by m. And so you can determine the subintervals from the rectangle and the upper bound. So it's minimum alpha is equal to the minimum of a and b divided by m. Okay. So basically this give you the existence condition. So it tells you that this is the one solution. And all right. I hope I can erase this part. It's okay. Fine, right? The second remark. So this is the first remark, right? So example. Example of bounded is like f of x, y equal to, suppose the function is x squared, and the rectangle is that x less than 1, y less than 1. So the center is 0. So suppose, for example, okay. So of course, in this rectangle, open rectangle, this function is bounded. Right? An example of unboundedness. Okay. Unbounded is like f of x, y equal to tangent x plus y, and all 0 is x over 2. Okay, and you can see that maybe I use s as the equation, x plus y is 5 over 2. Okay. So it's not rectangle, but because it's okay. And it's unbounded because the tangent pi over 2 goes to infinity. So this is unbounded. Okay. Now, second remark. Okay. And so the Lipschitz condition basically give you the uniqueness condition. Okay. Now, if f of x, okay, is partial derivative, okay, so if f of x has partial derivative, with respect to y, and r is 0, then the mean value theorem okay, I erase this one. the mean value theorem of differential calculus says f of x y1 y2 minus f of x y1 equal to y2 minus y1 and the partial derivative of x and y cubed. Where x y1 x y2 are in the open rectangle on 0 and the y delta is a suitable value between y1 and y2. Okay. So this is the mean value theorem for differential calculus. We learned from calculus. So in this case, and furthermore, if the partial derivative is bounded by 0, i.e. Then the function satisfies the Lipschitz condition in third. So this is third. Okay. Why? Well, because that if this has a bound, right? Then when you take the absolute value, then the absolute value of difference will be less than equal to the absolute value of the difference times n, and which is exactly the Lipschitz condition. Things. So this is the Lipschitz condition. Alright, so a sufficient condition to have the Lipschitz condition is that the partial derivative of f with respect to y is bounded. And this condition is much more easier to check, right? For you to check that. You just take the partial derivative of fy with respect to y. And then to see if this partial derivative is bounded. Okay? So don't be afraid of the Lipschitz condition. Okay? Don't be afraid of that. It is just that. So the example. I'm very sorry. Sometimes I drive into myself. Maybe someday you just remind me, okay? Yeah, you are very kind, I know, but you may have a class at 3:30, so you need time to walk to the other class. Okay, so I think I have to finish that. So this is the main idea about the existence and uniqueness of the initial value problem. Okay, so I hope you can read through the textbook. Okay, and I'm preparing a sketch proof of the theorem like this one. I'm preparing that. Once finished, I will send to you through the MS system. Okay, just for your reference. You have the time to read it. If you don't have time, skip it. Okay. I will not ask you to write a proof in the quiz or in the midterm examination. It's just for your reference. Okay. All right. So this is for today, and next Monday we will have quiz examination. Don't forget it. Okay. And the place will be here. All right. So this classroom. So next Monday, 7:30 to 8:30. Right. So see you next week.